Hello class. Okay, so today we're going to learn about linearization and differentials, and I'm trying to keep this video short, so I might not show all the work for the derivatives and other things, so you might have to like pause and restart the video to actually write them out. But linearization is usually pretty easy. It's the exact same thing as a tangent line. So if we come down here, another name for a tangent line is linearization. And there's a property called about differential equations says that they're always locally linear, which means if I like zoom in on any function, it looks like a line. So like if you graphed y equals sine of x and zoomed in on y equals sine of x, like here it's zoomed in, it looks just like a line. So if I zoom out, you can see that this function is y equals sine of x. So it's just a property. It's not something you really have to know. But the book might reference it, or a question on an AP exam might reference that a function is locally linear, which just means you can take the derivative. So the equation for linearization is the same as the tangent line, except they put L of x here instead of f of x. So it's still f prime of a, x minus a, plus f of a. So one extra thing we're going to do with tangent lines or linearization is we're going to use it to approximate the y value of function near the x value. And so for our first example, we're going to first compute the linearization of f of x equals the square root of x e to the x minus 1 and x equals 1. So I'm just going to write the tangent line for this equation. So we got to start by taking the derivative. Okay, so I took my derivative. I did product rule, don't forget that. The derivative of e is itself times the derivative of the exponent, which is 1, which I didn't write. Then I plugged in 1. Remember, I'm going to have e here to the 0 when I simplify, and e to the 0 is always 1. And then I added it, and I got 3/2. So that's my slope. I have to write the linearization, so it's the tangent line, so I also have to find f of 1. And so if I just plug in f of 1, I get 1 times e to the 0, which is 1, so I just get 1. So I'm going to write my linearization, or my tangent line. The only thing difference is I put L of x, so I put 3/2 x minus my a, which is 1, plus f of a, which is 1. So that's my tangent line. We've done that a bunch. They might ask you a little bit extra. So the next question says, use the tangent line to approximate f of 1.1. And y would be using the tangent line at x equals 1.1 be a good approximation, but not at x equals 6. So I'm just going to use L to approximate it. And to do that, I plug in 1.1 to L of x. And the reason we do this is this allows us to figure it out without a calculator. So most of these times, these problems will not be with a calculator. And so I'm going to plug in 1.1 into my L, and I can calculate this. So if I subtract it, I get 3/2 times 0.1 plus 1. And I'm better with fractions, so if I'm doing this in my head, I'm going to change 0.1 to 1/10, because then I can multiply it out in my head. Because if I do that, then I get 3/20 plus 1, and if I get a common denominator, I'm going to get 23 over 20. Okay, so this is my approximation, and the whole point of linearization is that we can approximate it without a calculator. If I plug 1.1 in here, it's impossible to figure out what the square root of 1.1 is, or e to the 0.1 without a calculator. So the second part said, why would using the tangent line at x equal 1.1 be a good approximation, but not at x equals 6? And I usually draw a picture to help me figure this out. So if I draw my tangent line around here, which I'm going to say is 1, we can see at like 1.1, which is really close, the tangent line is almost on top of the curve. So it's going to be a good approximation. But if I come out here, my tangent line's really far. So since x equals 6 is not close to x equals 1, L of x is not a good approximation for f of x at that point. The tangent line is far away from the curve at x equals 6. It's only close at the point that we write our tangent line for. Now part C says how accurate is the approximation of L of A plus 0.1 to F of A plus 0.1, and A is just 1. So we just want to compare like L of 1.1 if I plug in 1 for A and F of 1.1. This part you have to use a calculator, so I'm going to calculate F of 1.1 by just plugging 1.1 into my original function was up here, the square root of x e to the x minus 1. And if you do that, you get 1.159. And then store that value, guys, because we need it in a little bit. And then I'm going to just do L of 1.1, so I'm going to do 23 over 20 to make it a fraction. And then I'm going to subtract my two functions, and I'm 0.009 away. So it's a pretty good approximation. Okay, so another key thing we know about linearization is that it's either an overestimate or an underestimate. And so how we tell that is by looking at the concavity. And if you can remember that, you don't necessarily have to memorize it. You can just draw a picture to help you figure it out. So when f of x is concave up, if I draw a concave up function, and if I draw my tangent lines below it like I did here, we can see that the tangent lines are always below my curve. And so because of that, we say that linearization is an underestimate when my function is concave up. But when my function is concave down, it's the opposite. My tangent lines are always above it, so my tangent line is going to be an overestimate. So the only place it will give me the exact value is at the point that they share. But if I pick a point close to that point, the tangent line will be an overestimate when I'm concave down and an underestimate when I'm concave up. And many times linearization is used to estimate roots without a calculator. So it can estimate square roots or cube roots. So we're going to use linearization to estimate this. So we're going to write the equation of the tangent line. But in this case, we got to figure out a function, and our a, and our f of a. So if we look at this, we have square root of 27. So my function that we're going to deal with is the square root of x. And my x value is going to be 27, because that's what we want to figure out. But the issue is if I'm trying to do this without a calculator, I don't know the square root of 27. And so we could write the equation of a tangent line if we know the square root of this number, if we know the square root of the number, so that we can plug it into our function. So what's going to happen is we're going to pick an a value that's close to 27 and that we know the square root of, so that we can plug it into our or we can create a tangent line. And then if I plug in 27 to my tangent line, it will give me an approximation for what that value is. So the closest perfect square to 27 is 25. So that's going to be the a that I write my tangent line with. And so if I do f of a, f of 25, we know that's the square root of 25, which is 5. And then if I take my derivative, we get 1/2 x to the negative 1/2, taking the derivative of this. If I simplify that, I get 1 over 2 the square root of x. And then if I plug in my 25, we get 1 over 10. So that's the slope. We're going to write the equation then. So it's 1/10 x minus 25 plus f of 25, which we said was 5. This is the equation of my tangent line. So then if I pick my x, which we already know is 27, if I plug that into this equation, I get an estimate for what the square root of 27 is. Because L of x approximates f of x, and f of 27 is the square root of 27. So we would plug that in. And again, this would mostly be without a calculator. So if I plug this in to do the math, I get 2 plus 5. So I get 2/10 plus 5, which is 1/5 plus, and then if I get a common denominator, I would get 25 over 5, and that would give me 26 over 5. And so you could get this as a decimal with if you want, but this gives me an approximate of what the square root of 27 is. Cube root is the same idea. So if I do the cube root of 9, I want to create a tangent line equation or a linearization equation for a value that I know the cube root of. And so the value that I know the cube root of is 8. So I'm going to let my a be 8. And so what I'm going to do is I'm going to let my function be the cube root of x, because we're going to approximate f of 9 with L of 9. But we have to pick a perfect cube so that we can write the L of x equation. So that is 8. So we write our function, the cube root of x, that's x to the 1/3. You take the derivative and then simplify the derivative. So the derivative would be 1 over 3, the cube root of x squared, using my exponent properties. We're going to plug in 8, which is my a. And so when I do that, I'm going to do 8 squared, which is 64, the cube root of 64, which is 4, and 4 times 3, so my slope is 1/12. Plug it into my function. When we find L of 8, it's the cube root of 8, which is 2. So that's my f of a. And then you just plug in your x value, which we're trying to find, which is 9. So you plug in 9. And again, you solve it, simplify it, get a common denominator, and so I get 25 over 12. And that would be my answer for the linearization. So that's what all we're doing with tangent lines and linearization. The second things are called differentials. So we're going to do a differential equation. It's pretty much a derivative just rearranged. So when we do this, okay, we usually know our derivative is dy dx is the same as like f of x. They mean the same thing. And so a differential is just when we solve for y. So if we do dy equals, if we bring the dx to the other side by multiplying, we get f of x times dx. And this is called a differential equation. So it's pretty much just rearranged. And if you are continuing in math, if you go to like Calc 3, they do a lot with differential equations. And I missed something, sorry. Dy dx should be f prime of x, and this should be dy is equal to f prime of x times f of x. So make sure you fix that. That's a key thing. Okay, so our first example says find the differential dy and evaluate dy for the given values of x and dx. So we're going to use that equation. Okay, so we're going to use dy equals dx, equals f prime of x dx. Okay, so we need to find f prime of x. So we're going to find y prime, or f prime of x, which is 5x to the 4th plus 37. Because they give me an x value, I'm going to plug that in for x. So I'm going to find f prime of 1. And if I do that, I get 5 times 1, which is 5, plus 37, which is 42. That's my f prime of 1. And so my differential is just 42 times my dx, which they have to give you, which is 0.001. And then you may use a calculator for this to multiply it out. And we get dy is 0.42. And that's if that we're doing for this example. So that gives me the differential. So another way they write it, if they want like the function for the differential, is d tangent of 2x. And just remember, d dx means the same as dy dx, so they just kind of write it differently. So pretty much all they want you to do again, guys, is to take the derivative and multiply by dx. So just so if they rewrite it. So d dx of f of x is the same as f prime of x. And then they just rewrite it as if I multiply the dx to the other side. So d of f of x is equal to f prime of x times dx. And that's just another form of the differential. Okay. So when they write it like this, they just want you to take the derivative and multiply by dx. So the derivative of tangent of x is secant a squared of 2x times 2, and then we have to put the dx, and I'll just put the 2 in front. And that's it. Then you're done. The main thing differentials are used for is to make estimates. So our example 3 shows us that. The radius r of a circle increases from 10 to 10.1 meters. Use dA, which is the change in A, to estimate the increase in the circle's area. Okay, so we're going to write our differential equation. The key thing is dx means the change in x. So the change in x is from 10 to 10.1. So change in x means you subtract them, and the change in x is 0.1. So that's what dx is as a number. And so we want dA, and so that's our differential. So when we do that, we take our derivative, and we multiply it by dx. Now, they didn't give me an equation, so I have to like write the equation, and they told me the circle's area. So hopefully we remember the area of a circle. The area of a circle is pi r squared, and so I'm going to take the derivative of that. The derivative of that is 2 pi r, and then I'm going to multiply again by dx, because I'm just moving the dx to the right side since it's a differential. And then I'm just plugging in my values. So they said the radius of a circle increases from 10 to 10.1. We're going to use our original r, which is 10, in order to estimate the area. So we're going to just do 2 pi, my radius, which is 10, and then my 0.1 for my dx. And this will give me the estimate of the circle's area. And if you multiply those out without the pi, you get 2 pi. And so that is an estimate of the area's increase. And that is pretty much it. You're going to try some of the example problems in the textbook from section 5.5 that are on the calendar. And then after that, I'll go over questions tomorrow, and then we're going to start something called optimization. I hope you have a great night. Bye.